Okay, so today we're diving into a story of absolute audacity. I mean, how is a 2-year-old space tech startup out of Bengaluru attempting to master the undisputed holy grail of reusable rocketry? It's a fascinating tale of cutting-edge physics, extreme engineering, and this high-stakes race to completely redefine global space logistics.
But first, we really have to ask a pretty fundamental question. What actually is rocket science's hardest problem? Look, we all know putting things into orbit is incredibly difficult to begin with. But within the aerospace community, there's one specific engine architecture that stands head and shoulders above the rest. It's a concept that has literally taunted engineers for over half a century: the full-flow staged combustion engine cycle. Now, 800,000. Just let that number sink in for a second. That massive number represents the newtons of thrust produced by Astrobase Space Technology's newly unveiled EVEREST engine. We are talking about a true 80-ton class powerhouse here, designed from the ground up to utilize that notoriously difficult full-flow staged combustion architecture.
And honestly, the global stakes here are astronomical. Right now, this specific technology is incredibly rare. If Astrobase actually succeeds in flying this engine, India will join a highly exclusive club, taking a seat right next to the United States and China as the only nations to have ever developed and implemented this mind-bending propulsion technology.
Section 1. The hardest rocket problem.
To really get why this is such a big deal, you have to look at the stark contrast between the old way and the new way. In older, simpler engines, like the standard gas generator cycle, some of your precious propellant is essentially wasted. It's burned up just to drive the engine's pumps, and then it's dumped overboard as exhaust. But full-flow staged combustion, it demands 100% propellant utilization. Every single drop is routed through dual pre-burners and sent directly into the main chamber. It gives you the absolute maximum in efficiency, but it demands an unbelievable level of engineering. Let's break down the thermodynamics here, step by step. First, your fuel and oxidizer are sent to completely separate pre-burners. Step 2, and honestly, this is where the magic happens. Both of these propellants are completely gasified. Step 3, these high-energy gases drive the turbopumps. And finally, 100% of that incredibly pressurized gas meets in the main combustion chamber. Because everything is already a gas at this point, it mixes perfectly, which allows for massive chamber pressures and just unbelievable efficiency.
So, why exactly is this an engineering nightmare? Well, you're managing two fully gasified, intensely pressurized streams simultaneously. You've got a perfectly balanced fuel-rich preburner on one side and an oxygen-rich preburner on the other. And that oxygen side, it produces what aerospace engineers literally refer to as angry hot oxygen. It is vicious. It wants to consume and melt almost any metal it touches, which severely limits your material choices. There's zero margin for error here. If you get the balance wrong, the engine destroys itself in a matter of milliseconds. Because of all that, this has been a 60-year quest. The Soviet Union attempted it back in the 1960s with the RD-270, but it never flew. The US tested a demonstrator in the 2000s, again, never flew. It actually wasn't until 2019 that SpaceX finally flew a full-flow staged combustion engine, the Raptor. And now, jumping to 2026, Astrobase has stepped up to the plate, unveiling the EVEREST engine to take on this exact same legacy. Section 2. The Methalox advantage.
Now, Astrobase uses liquid oxygen and liquid methane, otherwise known as Methalox. You might wonder, why abandon traditional rocket-grade kerosene? It's simple, really. Kerosene leaves behind the sticky carbon soot that clogs up delicate turbopumps. Methane, on the other hand, burns incredibly clean. It's absolutely crucial if you want to build rockets that can fly, land, and then fly again over 100 times. Add in a highly efficient specific impulse of around 340 seconds, and the fact that we could theoretically manufacture methane on Mars one day, you can quickly see why it's the fuel of the future. And get this, EVEREST is designed to throttle smoothly between 50 and 110% of its rated thrust. You absolutely need this kind of controlled thrust variation if your goal is to slow a massive, free-falling rocket down through the atmosphere and stick a gentle vertical landing on a pad.
Section 3. Astrobase's Rapid Strategy.
To pull this off, they've put together a highly unique formula. At the helm, you have Devakumar Thamasetti, a veteran propulsion engineer from ISRO, paired up with Neeraj Khandelwal, a highly successful tech entrepreneur. They're combining deep aerospace expertise with agile tech startup capital, including a massive $10 million seed round and a 25 crore rupee government grant.
Plus, they aren't just doing this on paper. They already have a 46,000 square foot plant in Bengaluru and a massive 21.5-acre test site in Anantapur.
To move fast, they're embracing some seriously cutting-edge manufacturing. By partnering with Wipro 3D, they're utilizing India's largest industrial metal 3D printers. This is a total game changer because it allows them to print intricate internal cooling channels and complex engine geometries that would be literally impossible or prohibitively expensive and slow to create with traditional machining. It allows for the rapid iteration that is just the lifeblood of a modern aerospace startup.
Their timeline is frankly incredibly aggressive. They've already completed subscale hot fire tests, crucially utilizing the official ISRO propulsion complex down in Mahendragiri, which is a prime example of public-private partnership in action. They completed their turbopump trials in early 2026, and their plan right now, hot fire tests roughly 20 individual full-scale engines to ensure absolute reliability, all pointing toward a targeted first orbital flight in December of 2028.
Section 4. India's private space boom.
To put things into perspective, the global launch bottleneck right now is stark. When it comes to active satellite fleets, the US has over 12,000, China has over 1,400, India currently has fewer than 100. Companies globally are waiting in these massively long queues just to get their hardware into orbit. If India wants to capture a larger share of the global space economy, it desperately needs indigenous, reusable, medium-lift rockets.
And this is exactly where the government stepped in, creating the precise environment needed for this boom. The creation of IonSpace as a single-window regulatory body acts as a promoter, enabler, authorizer, and supervisor all rolled into one. It finally opened the doors for private entities to step up and build real space infrastructure, effectively ending decades of state monopoly.
And they aren't just talking, they're backing it up with actual capital. Just listen to what Rajiv Jyoti from IonSpace noted regarding their Technology Adoption Fund. He said, "This capital was set up precisely to enable the private sector to undertake such innovative technologies and technically demanding work. The government is actively investing in Astrobase's ambition to crack the FFSS engine."
Because, if they actually crack it, the scale is just incredible. Astrobase's ultimate vision is to transition the Indian private space sector from simply offering small launch cabs to space into providing heavy-duty space logistics. They're eventually aiming to put 1,000 tons of payload into orbit annually. I mean, that completely changes the economics of access to space.
So, I want to leave you all with this provocative thought. Will mastering these highly complex, reusable medium-lift rockets ultimately be the key to truly democratizing access to space for everyone? It's a massive challenge for sure, but the payoff could change everything. If you want to dive deeper into the physics, the funding, or the timelines we covered today, be sure to check the links in the description to read the full source articles. Thanks for joining me on this explainer, and keep looking up.